Go.
All right, perfect. Hello everyone, and thank you for attending today's seminar at the Robotics Institute at UofT. Whether you're attending in person or through the YouTube live stream, welcome again. It's a beautiful day outside, so it's a pleasure to see everyone here. It's for a good reason. So we're lucky to have Professor Dmitry Berenson as our invited speaker today from the Department of Robotics at the University of Michigan, where he directs the Autonomous Robotic Manipulation Lab, or ARM Lab. Great name. So Dmitry is known for his work on developing general purpose algorithms for planning, learning, and control for manipulation. His work is also known for its rigor and careful development of theory and methodological advances, but also for its careful experimentation and validation on real robots. Dmitry has worked on several topics of interest, including but not limited to deformable objects, tool use, safe planning, control, and grasping, as well as locomotion and perception. And in order to accomplish this, Dmitry and his students draw ideas from search optimization, machine learning, motion planning, control theory, and topology to prove the properties of the methods that they develop. Dmitry did his PhD at CMU with Sid Srinivasa and James Kuffner of RRT fame, for younger people in the audience, and his postdoc at Berkeley with Ken Goldberg and Peter Abil. Dmitry's work has been recognized with many awards, including the IEEE Robotics and Automation Society Early Career Award and the NSF Career Award. So without further ado, I'd like to welcome Dmitry to Toronto, so the stage is yours.
Thank you so much for Thank you for that very kind introduction. Can everyone hear me okay in the back? Great. Okay, so I'm Dmitry, and I'll be talking about two topics today: where to trust and how to adapt models that we learn for the purpose of motion planning. So if you could pick one question that kind of underlay every project, almost every project I've done since starting my PhD, it's this one. Basically, how can a robot automatically generate motion in unstructured environments? And really the key word here is unstructured. If we know the environment a priori, and we have a lot of computation we can do knowing that, that's generally not a problem I focus on. I really try to focus on questions of the robot is deployed in a new scenario, and it has to do its best to use whatever it knows or to apply whatever general algorithms it has to that scenario. So how do people in general go about answering that question, generating motion in these unstructured environments? Well, traditionally, there's been a very standard set of steps that are followed. So the first step to generating motion in these kinds of difficult environments is to get data. Right? So somehow, let's say you want to model the behavior of how this car drives on snow and ice. So I need to get a car and I need to drive it around on snow and ice. I need to instrument, I need to get a bunch of data. And then from that, I need to look at that data and I try to understand the underlying structure of that data. And I try to write it down mathematically in terms of some kind of dynamics function, okay? And then, of course, I don't just trust that I know the right function. I have to simulate it, I have to compare it, I have to write a controller around it to see if this is how the controller works with this kind of dynamics. I do all of these things, and I look at it again, and I say, okay, is that good enough? Because it's never perfect, right? And I iterate this loop, I run this loop many times until I'm happy. Once I'm happy, then I can use that dynamics function in many different places, not just in the specific scenarios I collected that data. And I can use it in control. I can do optimal control with it, for instance, or I can use it in planning, longer horizon trajectories using all sorts of motion planning methods. But now I have this dynamics model, okay? Now, this approach does have limitations, even though it is still very strong and probably most reliable approach we have. And the problem is that when the dynamics become very difficult, meaning there's a lot of uncertainty, there's multimodality, there's even a lack of perception that is hindering us from creating that model, this process becomes very, very difficult. And so a lot of people over the last few years, maybe even as long as 5 to 10 years, have switched tack, and they said, okay, we're not really going to rely on a human engineer in the loop looking at data to construct our dynamics models. What we're going to do is collect tons of data. Okay, we're going to collect data like at the Google ARM farm in the real world, or perhaps in simulation if we trust our simulation models are good enough. We're going to collect that data and we're going to feed it into some sort of learning method. Now here I drew a neural network. It doesn't have to be a neural network. It can be a bunch of other things too. But at the end of the day, that method is going to give us either a dynamics function or more commonly just a policy that I can directly apply. And many of you that I've talked to today are doing some form of this, including myself. I also do some form of this. Now, just as a side note, everybody knows that there's a lot of thinking here. I think in the media that gets billed as, oh, it's just all automatic and stuff. But we know there's a huge amount of work in designing the environments we get data, designing the networks, and even just evaluating whether our method is working. It's not like reward functions fall out of the sky. Somebody has to create those, right? So we know that. But even given that, there's still a problem with this kind of approach in that for these kinds of manipulation tasks, at least, it's really unrealistic to ever say we've got enough data for everything we want to do with this robot. I could always come in with a new object, a new task, and your model would have trouble there. And this isn't just a theoretical concern. I think probably many of you are familiar with OpenAI, really amazing company. ChatGPT was a major breakthrough, right? But I was really fascinated with this article that I read. This is now 2 years ago, where the founder of the company, it says, quietly revealed that it shifted its focus away from robotics, basically closing its robotics effort, and focusing on domains where data is more readily available. And now you see ChatGPT turns out a good move. Okay, but this is saying something to us that this ability to not get enough data for robots is not just an academic concern. This is a real world problem, and it's causing companies to radically change what they're doing. Okay, so if you're kind of buying into this, then I think, to really state that clearly, I'm making a proposition that the models that we learn are going to be perhaps useful for some tasks and states and so on, but it's never going to be the case that I just take a model and I deploy it in the real world with no additional training, no adaptation, no fine-tuning, and it just works. That's the proposition I'm making in the talk today. Now, if you accept that proposition, then there are two questions that instantly come to mind. The first is, well, if it's not going to be reliable for all the states and actions that could occur, then where is it reliable? I mean, it's got to be good for something. So that brings up the question of where can we actually trust our models to give us accurate results? And the other question is, well, you said that you want to explore these tasks in more open-ended environments, new tasks that you haven't seen before. So how are we going to adapt these models that are imperfect to new tasks that they haven't seen? I think these are the two most relevant questions to be asking if indeed you accept this proposition. So that's what I'm going to talk about today, and I'll talk about one paper that is one of our approaches on each of these questions. Okay, so let's start with where we can trust our models. So this is the work of Craig Muth and Glenn Chu, co-supervised with Neshme Oze. And this is a work on when we want to learn a dynamics model that we want to use for planning. And just to motivate it, I'm going to show an example of a learned dynamics model that is leaving the domain of the training data. So we got some training data to learn the dynamics of this arm, and now we want to use that model in order to plan a path to get to the goal. And as you can see, even though in planning we actually did compute a valid path given our dynamics model, when we execute it on the ground truth simulation, we get a terrible result. Okay? Whereas, if we could stay in the domain where our model is valid, basically near enough to the data, and I'll get much more into how near enough is near enough, then it actually does pretty well. It tracks the plan it produces pretty closely, and it eventually reaches this goal. Okay, so staying where your model can be trusted is, in my view, not optional. It's not like, oh, we'll just have a little bit of error. I mean, that could happen, but it can also lead to absolutely catastrophic error if you don't stay where the model can be trusted. And so then the question becomes, how do we guarantee that we're going to safely reach this goal when we plan with a learned dynamics model? Now, I want to say that you know, the issue of model error and uncertainty and so on is a deep issue that's been studied for many, many years. We're not the first people, not even close to look at this kind of question. I mean, there's been work on safe reinforcement learning where, you know, you assume you have a kind of partially known safe controller and use techniques like GPs to infer model error and so on. Those have limitations around these assumptions. We've done work on motion planning with learned models. This is an image from our papers, but so have many other people. And this works, but really has no guarantees. And so you just end up picking tasks that are kind of like what you saw in the training data. And everybody does this. I do this. I'm not saying it's a bad thing, but you know, we want to try to get a little bit beyond that. And there's also a huge amount of work in control. And I don't have nearly enough time to talk about all of robust control here, but there are many methods in this robust control literature that are looking at error in your model. Unfortunately, oftentimes they require very strict requirements on the form of the model, or they require very tight bounds on the error, and just setting a kind of overall worst case error usually ends up being too conservative for the kinds of tasks that we do. So in contrast, the method I'm going to present is a way to empirically estimate the model error from data and use that to make statistical guarantees. And then we're going to use that kind of estimate of where a model is valid that emerges from this to actually plan trajectories that we can have some guarantee, again, statistical guarantee of tightly tracking. Okay. So to make it a little bit more concrete, here's the problem we're trying to solve a little bit more mathematically. We're given a data set of x's and u's, x's are states, u's are actions, and the result of applying a dynamics function. This could come from a simulator. Ideally, it would come from the real world. But the system is unknown, so we don't know what f is. So this function right here, f, is unknown to us, though we can get these kinds of samples of its output. And then what we want to do is estimate the dynamics as best we can using an estimate G, and then guarantee that when we execute what we planned in the true dynamics, in the true, let's say, real world dynamics, it's still going to work. Now, that problem sounds way too hard, right? Because we don't know f, we just get samples from it. But if we make some assumptions, we can actually tame this problem a little bit and make it track. So the first is that the dimension of our state space x is the same as the dimension of our state space u. This is actually not related so much to the learning issue as it is to the controller we're going to use. In later work, which I'll talk about very briefly, we've relaxed this assumption and allowed under-actuated systems as well. But for now, we're going to stick with that. We assume deterministic dynamics. This is actually quite a hard assumption. We don't have stochastic dynamics in this framework. We assume the system is controllable and that it's Lipschitz continuous. Okay? So if we can make those assumptions, then we can apply our methods. The key difference, though, from prior work is that we have absolutely no assumption on the dynamics model structure. So you'll see that our dynamics is actually a neural network, and we really just treat it like a black box. And the other key difference, I think, from a lot of the work, mainly on the control side, is that we're not really restricted to low-dimensional systems. You'll see a system basically that has 7 states, 7 actions, so the state action space is 14-dimensional. So not a trivial system. Okay, so our method has 3 parts. The first part is that we're going to learn a dynamics of a specific form here. This is called a control affine dynamics. So you actually learn 2 functions. One is purely of state. Actually, both are purely of state, and then you multiply the second one by u. That's how you include the control. So this is the form of dynamics we're learning. Again, what the model itself is, what produces G0 and G1 is just some neural networks. No real assumption on what those are. We're going to use very standard methods to this. Your machine learning 101 tutorial, you give it x and u as input, it predicts x t plus 1. Nothing really special there, so I'm not going to go into details on this. The main part of the method is this. I'll go into a lot more detail about this, is that once we've learned this dynamics model, we need to actually tell you where that dynamics model can be trusted. And we do this by constructing what we call a trusted domain in state action space, so XU here. And we do that by computing what we call, well, not just us, but what is termed the Lipschitz constant on the error. So we're going to have a error function that's the difference between the true and our estimate, and we want to bound the Lipschitz constant of that function. Once we have this trusted domain based on these Lipschitz constants, we can plan inside that domain using an RRT-based motion planner. It doesn't have to be RRT, but that's what we use. And the big advantage here is that if the assumptions are met, we can guarantee tracking on this system. So if you compute a plan, you are guaranteed to be able to track that plan within a fixed epsilon of error. Yeah.
And does this require you knowing the Lipschitz constant of your neural network or bounding it somehow?
Not explicitly, no. We're going to do it all through samples. Yeah. Okay. So the key parts of the method that I'm going to talk about are here. So first, how do we estimate these Lipschitz constants on the model error? Second, how do we use those to create a trusted domain? And third, how do we use this in planning and in our execution, creating a feedback law? And then I'll talk about some experimental results. Okay. So let me break down this problem of identifying this Lipschitz constant on the error with a simple example. Okay, so let's say that we have our true, this is a very toy example, we have our true dynamics function, takes as input the z, output z prime, and it's this gold line. So it's not a linear function, okay? And now I'm going to sample some data from this true function, those are the green points, and then I'm going to do a least squares best fit of a line to that data. This is very, very simple. This is not what we actually do, this is just to demonstrate the concepts, okay? So what can we say about the error of our model? Well, in order to figure that out, we need to define some terms. The first is the maximum error on the data. So this is how much error I can actually get on the data set I'm given, the maximum of that. Okay, then the trusted domain is something I'll define later, but the trusted domain is basically where I think the error of my model is below some epsilon. And then I also need the dispersion of our data set. We call this BT here. If you don't know what dispersion is, it's the radius of the largest empty ball. So it's basically how big are the gaps between my data. And then we have what we call the local Lipschitz constant of the error. That's LF minus G, right? So F is true, G is estimate. This is the Lipschitz constant of the error. And if you don't know what a Lipschitz constant is, it's basically a bound on the ratio of changes in the output versus changes in the input. Okay? So that's what we need. And we show in our paper that if we have these quantities, then we can actually write down this relationship. It's done via the triangle inequality. I'm not showing you the derivation, but it's fairly straightforward. It's in the paper. So the upper bound on the difference between the learned and the true dynamics is this epsilon. This epsilon is a function of these other variables, and it's only valid in this trusted domain D. I haven't told you how I made D yet, but you'll see that later. Now, if you look at this formula, the big problem is that we don't know this Lipschitz constant, right? These are things we can compute from the data. We can't just look at the data and get a Lipschitz constant. It's a little bit more complicated. So given a trusted domain, how would we even estimate this Lipschitz constant? Okay, so let's try a simple way to do this. Okay, let's say we have some domain D of data. We want to estimate the Lipschitz constant of the error in this domain. So you might say, okay, well, let's take a bunch of pairs of data, right? Because the Lipschitz constant is evaluated between two different inputs. So our inputs are pairs of x and u. Let's look at two pairs of data, a pair of data, and evaluate the model error. So we can compute the model error because we have the ground truth for that data. And then we can calculate the ratio between the change in the error and the distance between those points. And that, turns out, is one way to try to estimate the Lipschitz constant. And you can do this by sampling many, many points, and you just compute this Lipschitz constant, and then you take the maximum. And that should be a bound on the Lipschitz constant, right? Wrong. This is the first thing we tried, and then we learned this is actually guaranteed to be wrong, right? The reason is that you're guaranteed to underestimate the Lipschitz constant in the general case. Imagine that there's some pair of data points over here that you haven't sampled. That's actually the worst case Lipschitz constant. Your probability of sampling that is 0, right? Unless there's a set of sizable measure of exactly that Lipschitz constant, which is not true. So you're always going to be approaching the upper bound from below and underestimating it, and you can't make any guarantees. So really what we want to do is we're never going to get the exact Lipschitz constant, right? Because you'd have to sample that specific pair of data points. So instead what we want to do is overestimate. And how do we guarantee we overestimate? Well, we can make a probabilistic argument that we can overestimate in the limit. Now, the argument that I'm going to make is absolutely dependent on this very cool theorem. We call it the FTG theorem, just informally stating it here. This theorem says that the distribution of the maximum of a sample of IID random variables can only converge to one of 3 kinds of distributions in the limit. Now, in the limit is important here, right? So this is statistics. Things are valid in the limit. That means I need to have enough samples. And in our specific case, we actually know a little bit more because the only distribution that makes sense for us is this reverse Weibull distribution because it has a finite upper limit. The other two don't. Great, so we can apply this theorem from statistics and we can use that to estimate our Lipschitz constant. And here's how we do it. Again, we sample a set of pairwise ratios of the model the model error by sampling data points and computing the error and the distance. And this is done in a validation data set. This is not the data set we trained the dynamics model on. And then we can fit a reverse Weibull distribution to the statistics of what we're to the data that we're sampling here. And we're using this 3-parameter Weibull distribution, and basically one of the parameters is this gamma, which is the upper bound, how can I put it? The upper limit on the support of the distribution, okay? And then we can check if we're getting a good fit using just the standard KS goodness of fit test. And then, by the way, I should mention that this process is actually similar to some previous work in machine learning on generating adversarial attacks on neural networks. Then what we can do is put a confidence bound on the Lipschitz constant we estimate, right? So what we want to do again is overestimate. So we're going to overestimate with a certain confidence level we call rho. Basically from this we can produce a guarantee that the probability of our Lipschitz constant being valid is greater than or equal to this rho, and rho is something you set. The higher you set rho, the closer it is to 1, the more samples you're going to need. Not surprising. Okay, I know that was very abstract. I wanted to show you just concrete toy example, right? So let's say I have this function which is just z squared, right? And I want to estimate the Lipschitz constant of the error in this domain D. I can sample pairs of points and compute the error, just as I talked about before. And this is what's shown here is fitting that reverse Weibull distribution to the maximum of those samples. As you can see, as we get more and more samples, this bound tends to get closer and closer to 2. And 2 is, in fact, the upper bound of the Lipschitz constant. Okay, so now that we've got our Lipschitz constant, we have to say how we're going to generate that trusted domain D. And it's actually an iterative process where we estimate a domain, get a Lipschitz constant, estimate a domain, and so on. So let me tell you how that works. So let's say we have a set of data points that we use to train our dynamics model. So these are not the ones I said for validation. These are used to actually train the model. And the first step we do is that we know the model is not going to fit every data point perfectly. So we're going to just make life easier and throw out the data that is very, very high error for the model that we run. Okay, so we get rid of that. And what we want to then do is build a trusted domain in this state action space XU by putting a ball of radius r around every data point that remains after we throw out the high error ones. Okay, so our trusted domain is just a union of these balls. It doesn't necessarily need to be connected. Okay, so there's nothing to enforce that here. It's just a union of those balls. Okay, so how do we then figure out that R? Well, we initialize R to kind of heuristic initialization. And then we can estimate this Lipschitz constant with the domain that this R gives to us, right? So if R is too big, then our Lipschitz constant is going to be really huge, and we won't be able to make useful guarantees. However, if R is too small, a Lipschitz constant might be good, but we're not going to be able to plan. So getting a good R is very, very important. So the next step here is we're going to make sure that the Lipschitz constant here is greater than or equal to 1. If that's not the case, we're going to return failure. Now, this looks very strange because in the Lipschitz world, there's nothing special about the number 1. Okay, you can have a Lipschitz constant of 1 or 10 or 5 or 0.1. It's all fine. But this is actually very important for how we use the trusted domain in our motion planner because we're going to be sampling configurations within these balls. And if we have this fact, then we can make a very efficient conservative check to see if a sample is going to be valid or not. Whereas if the Lipschitz constant were smaller than 1, you could still make a trusted domain, but it becomes very expensive to check if a sample is within that domain. So I'm not going to get into the details of that. If you're curious, I have a slide on it. We can talk about it after the talk. Yeah.
So regarding the connectivity of this cover,
yeah.
Doesn't random graph theory give you a threshold for the radius after which you have connectivity with probability 1?
Yeah, great question. So why can't we figure out the connectivity of this? And I think we could probably use something like that. It turns out that for what we want to do, it's not really that the space has to be completely connected. Like imagine there's a data point over here that's just not connected to the others. Well, unless I'm trying to get from here to here, I don't really care, right? What I care about is that I can get from my start to the goal within this trusted domain. So I'll talk more about how we do that a little bit later. So we don't actually require the space to be connected. Okay, so once I get the, once I have this estimate of the Lipschitz constant, then I can estimate this error epsilon, right, which is my error upper bound using that formula I showed you earlier. And if R is greater than epsilon, then I'm pretty much done because again, I'm trying to make the ball big enough to capture the error that I would have. If it's big enough, that's good enough for me. Otherwise, if R isn't big enough, I increase R and I just redo this loop. Okay. Now, this is what I mentioned about having an efficient nearest neighbor check. Again, can go into more details later. Don't have time to get too far into it. Okay, so now that I've got this trusted domain, how do I actually do planning and guarantee something about the execution? Okay, so our method is called Learn Models in Trusted Domains, RT. It's a bit of a mouthful, but I really want to emphasize that this is not an RT method, right? This is just using RT as a way to generate actions. You could use your favorite trajectory optimizer, MPPI or CEM or whatever, and you can do the exact same stuff, but we used RT here. Okay, so in order for the RT to stay within the trusted domain, you have to basically check two things as you generate new states and actions. The first is that each XU that you generate along the trajectory has to lie in a set that is strictly smaller than D. And here's what this looks like. Basically, imagine you have this trusted domain D, and you could carve out a ball of radius epsilon away from the boundary so that you are always at least epsilon from the boundary. Right? So this creates a set D epsilon. If we stay in D epsilon, we're guaranteeing that our state will never leave D. Okay? So that just shows you that ball there. Excuse me. Now, you can then use the nearest neighbor check on your data set to see if a new sample you generate, XU, is contained within D epsilon. You find the nearest neighbor, you look at how far it is. If it's less than epsilon, you're good. If it's not, then that's not a state in action that you can use. Okay. Now, the other thing we have to check as we're planning is whether or not a one-step feedback law exists. Again, I'm not going to get into the details for time here, but basically we're using a very simple controller that's based on least squares, and it allows us to guarantee that our system will stay where the model error is below epsilon, and thus that the system can be stabilized in execution. In order to check if that's the case for a given sample, we have to basically compute what the feedback would be and make sure that it's also within the control bounds. So we have to do that check and this check, and then we can make our way through this trusted domain D as we're planning. Here's just a really simple cartoon of that, right? We're starting at some start, but we're trying to get to this goal region over here, and we're trying to move through this set D epsilon. This is just the state component of it. It has an action component, but I can't really draw that here. And there are, of course, some obstacles in state space. And so what we do is we sample actions that we roll out to get states, and we check, is the XU we got here inside of D epsilon? If it's not, then we just reject it because we don't know if it's safe or not. If it is, then we keep it. Sometimes we'll sample something that's inside, but the controller requires too big of a action to actually do this, so we have to reject that. We keep planning. We reject things if they're near collision, and eventually we get to the goal. Okay, so that's a very simple cartoon, but let me show you how the execution works, and then I'll show you how the results look. In execution, like I said, we have this one-step feedback law that's just looking at trying to get to the next state, right? And what we've done here is we've planned a trajectory using our dynamics function we learned called G. And now we're trying to execute it on the system F, and F and G are different. There's error between them. Now, so what's going to happen, as soon as we take our first action, which is U0, we are going to end up at a different state than what we planned, right? This is the nature of the error in the dynamics. Our guarantees and the checks within the planner ensure that the distance between this state and this state is less than epsilon. Great, but if I just keep executing open loop, I'm going to diverge, right? Even though the first step is good, the next step won't be, right? So what I have to do is correct for that error in my next step. And that's what that one-step feedback controller does. It says, okay, I'm here. Now I'm going to apply feedback because I know I'm off where I'm supposed to be. Again, based on G, right? I'm going to apply feedback to get to X2. And then our guarantees ensure that, again, we don't get to X2, but we get within epsilon of X2, right? And then we just keep running this process over and over again. We keep trying to fix the error, we keep diverging, but we stay within epsilon of the states we plan, and eventually you get to the goal this way. The goal within bound of epsilon. Okay, so there's a couple theoretical guarantees in the paper. I want to talk about the most important one here, which is the following. First, we're saying that if we have this one-step feedback law for each transition, and the Lipschitz constant estimates are valid, I talked about the conditions for that when I talked about that reverse Weibull distribution, then this system tracks the plan with epsilon accuracy. Just to make it totally clear, in the limit of infinite samples for this Lipschitz estimation, this feedback law guarantees that the trajectory is safe and will reach the goal. with a certain probability. And that probability is basically how valid each Lipschitz constant is. And if you assume each one is valid with probability rho, then you get rho cubed. Okay, so let me show you a few of the experimental results. So we tested on a 6D nonlinear quadrotor model. So this is, very tricky dynamics to learn, I think. A Sevendorf-Kuka Iowa arm as well. And we compared to some baselines, like just executing open loop without that feedback controller, or just trusting this model everywhere, just assuming it's correct. As I said, we're doing very simple methods for actually learning the dynamics equation. And so here's what it looks like for our method, right? You can see red is the nominal plan we computed, green is open loop, blue is closed loop. And they're all pretty close. And you'd say, well, why do you need this blue controller if your open loop is already close to what you planned? The reason is we're staying in that trusted domain, so we wouldn't expect the error to get high. But that is not always the case, because if you plan without the trusted domain, you get this. Okay, so the red is a perfectly good trajectory that was planned, but if we try to execute an open loop, it goes crazy. If we try to stabilize it with our controller, it doesn't do well either. Okay? So this method is really important for staying inside the trusted domain. If you leave it and use exactly the same dynamics model, your actual system will diverge.
Sorry,
yeah.
The stabilizing controller is MPC or something else?
So for this method here?
Yeah.
Yeah, good question. I think we used a fairly simple controller, but I'm not remembering exactly which one it was, so I'll have to look back at the paper and get back to you on that one. Okay, so this is a example for the ARM environment, and this is a particularly bad one, I'll admit. It's not always this bad, but this is, again, just showing if you have this nice nominal plan. I'm sorry, this is our method. This is great, this is not a bad one. Sorry, I got the order of the slides back. But anyway, if you have a nominal plan and you execute open loop and closed loop too, you track the plan quite well using our method. This is what I thought I was going to show you. This is if you don't do that, right? So the nominal plan can look fine, but then the closed loop execution does poorly, the open loop starts bumping things, and you don't reach the goal. As I said, this is a particularly bad one. It's not always this bad, but you can look at the statistics and you'll see that when we use this naive method of just trusting the dynamics everywhere, we actually do significantly worse, sometimes like orders of magnitude worse than when we use our method. Okay, I want to say very quickly that we've extended this to underactuated systems and we've made spatially varying bounds. We've used a much more sophisticated controller than that least squares one. This is in a follow-up paper that was published in CDC. I don't have time to go into it, but it allows us to control this dynamic quadrotor. You're seeing it just in the plane here that's underactuated. It allows us to do things like pulling a rope based on demonstration data. So this is a plan that's synthesized using fragments of demonstration data, and we can guarantee that even for this 22-dimensional state, we can reach the goal within a bound of epsilon. Okay, I don't have a ton of time, so I want to kind of go a little bit faster through the second part of the talk, which focuses more on this question of how do we adapt our models to new situations. Now, in this part of the talk, yes?
Excuse me, I have a question regarding the last.
Could you just hold that for the end? I'd love to hear it, but I want to get through this. For this question, we're not going to be learning a dynamics model. We'll be learning how to sample good trajectories if we know a dynamics model. Okay, so here's our problem, and this is actually the model predictive control in the sampling-based view, the model predictive control problem in a nutshell. So we have a problem where we have black box dynamics. Again, we don't know much about the dynamics equation, can't use very specialized methods, and we need to plan a trajectory quickly. Ideally, we want to replan it every time step, so speed is really important here. And we need to handle cluttered environments. The real world is not a big open plane where we just drive without care for hitting anything. And we're not going to know the geometry a priori, so we can't get lots of data on that specific environment. Okay? So there are a lot of sample-based MPC methods. I should include citations here, but you'll see citations later, that basically take the following approach and different variants of it. But basically what they're doing is they're sampling a set of action sequences around some nominal sequence. They roll them out, so they compute the trajectory of states that results, and they compute the cost. And then based on the cost, they repeat this process, but they bias new samples toward low-cost trajectories, right? So every time you repeat, you get closer and closer to a low-cost trajectory with your samples, right? There's a limitation to this, though, and really it comes from this cluttered environments issue here. So in cluttered environments, it can be the case that the probability of sampling a low-cost action sequence, especially with a finite horizon, can be very, very small. And here's an example of that exact case. So here we have a double integrator model, and it's moving through this environment. These hazy things are the sign distance fields of obstacles. So basically we want to stay yellow. We don't want to go into this like green and blue stuff. And so the robot tries to drive toward the goal, and it's making progress, but in here we get stuck. We can't find any good trajectory samples that get us around this obstacle. Okay, so this is the work of my student Tom, and Tom basically had the following contributions in this paper on this topic. First, what we wanted to do was not just sample naively around low-cost trajectories like this. We wanted a more informed sampling that actually is aware of the start, the goal, the environment, right? So one of the key steps here was to learn a sampling distribution using normalizing flows. And this sampling distribution is trained to generate goal-directed and environment-aware sequences of controls. Now, that's great, and it's interesting in its own right, but what I'm really excited about in this work is that we also have a method of adapting all of this stuff to new environments that are radically different from the environments we trained on. So I'll show you examples of that. Okay, so a little bit more on the fundamental MPC problem. We have states, actions in our trajectory you see there. Our dynamics can now be stochastic, right? So we have input x, t, ut. We're trying to predict a distribution perhaps over the resulting state xt plus 1, and we have some cost function j on trajectories, right? So we start at a certain start, we're trying to get to a certain goal in state space, and our objective is then basically to find the u that minimizes the expectation of the cost under these dynamics that we have here. Now, the dynamics can also be deterministic, and in our system they are, or they can be stochastic, either way. Okay, so what we are going to do is, again, start with some nominal trajectory, could be from anywhere, sample around it, right? Compute the cost of those samples, and then hopefully find a better trajectory, sample around that, and so on. But in the presence of obstacles, as I said before, all those trajectories can become bad, and then we don't know what to do. Okay? All right, so the key issue that we saw in this work is that our sampling distribution is very naive. It's just a Gaussian, right? We're just adding Gaussian noise to a nominal trajectory. That's how we produce our samples. This is true of MPPI in particular. What we want to do is have a much more informed distribution, a distribution that doesn't just have some mean and covariance, although those contain some information that is updated as you sample. We want to actually explicitly include knowledge of the start and the goal and the environment in our distribution for generating these sample trajectories. So that's our goal here, to basically figure out that. Okay. Now, how are we going to figure that out? Because we don't have any true distribution. Like, we don't have this function written down somewhere to use as ground truth. So what can we do? Well, we can apply variational inference. And we're not the first people to approach MPC from a variational inference perspective. Maybe you've heard of Stein variational MPC. It's another way to do it. But the idea here is that we're going to define an optimality variable O, which is basically the negative of the cost function that you see there, the probability over it. And what we want to then do is find the posterior. So given that our trajectory is optimal, what is the state and actions, what are the states and actions that produce that optimal cost? And of course, we don't know that directly, so we're going to create an approximate posterior, which is going to look like this Q that factorizes, as you see there. And so then our objective is to basically minimize the KL divergence between this approximate Q and the true distribution. But of course, we don't know the true distribution. So what we have to do is look at it sample-wise, right? So we look at a certain trajectory, and then we can try to minimize this. This is the entropy here, and we're trying to basically minimize this expression. I'm going a little bit fast, so the idea here is we want to both minimize cost and maximize the entropy. Okay, so there are many methods for variational inference. One of the most popular is modern methods, I should say. It's a variational autoencoder. Many of you, I'm sure, have heard of this. But it's the idea that you take your data, whether it's images or trajectories or whatever, you encode it to a distribution, and then you can, and it's usually a Gaussian, by the way, and then you can sample from that distribution, decode the sample, and you've got a basically generative model that can produce similar things to what you've seen. Right? And you basically train this model by maximizing this elbow loss. But the key problem with variational autoencoders is how you actually compute this term. So this is basically what the decoder is doing, the probability of the data given Z. You need a way to compare the input and output data, essentially. Traditionally, especially in the computer vision world, they use reconstruction loss. And that's okay, but it's sensitive to like small changes. Like if I predict a line here, and I reconstruct a line that's 1 pixel away, my reconstruction loss is huge. But that doesn't really make sense, right? The problem with this kind of loss is it assumes this independence of the elements of X, and it can be hard to capture the dependence. So there's a lot of issues to work out to apply a VAE. Though we will apply it for a different part of our method. Another method that is a little bit more recent that we're very excited about applying in many robotics contexts is a normalizing flow. And a normalizing flow might look a little bit like a variational autoencoder in that it produces a point in a distribution, but it has a key feature. So a flow is basically a function that maps from your data to what we call base distribution. And this function f here must be invertible. If it's invertible, and I can map from data to this z, then I can map from samples in the space z to data, right? And in fact, because it's invertible, I can guarantee that I get exact reconstruction of my data by default, because it's an invertible function. Now I have to define this base distribution. Usually it's a Gaussian, sometimes it's uniform. It's usually a very simple distribution. And now I don't need that reconstruction loss. I can actually train by maximizing the log likelihood of the data directly. There's no reconstruction happening. So that's a nice feature. Now, life is rarely that kind. So it has those pros that I talked about. It does fantastic for generative model. If you've seen Glow, now it's a little bit old, but amazing images that it generates. But there are some cons, right? So the form of f has to be restricted to be invertible. And it's very finicky to train because these networks tend to be huge. You don't get any dimensionality reduction like you would in a VAE. The dimension of this has to be the same as the dimension of this because it has to be an invertible function. So those are issues, but they're overcomable. Okay, so how are we going to apply all that stuff to our problem? So we have this control problem, remember, of getting from start to goal without hitting obstacles. The first step is to get the inputs and turn them into methods that we can actually use. Here, this is the environment, and we're encoding it basically as a signed distance field. We're transforming it to a signed distance field, and then we're putting it through an encoder. That's giving us a, this image screwed up in my slides. This should look like a Gaussian. So we're encoding it to a Gaussian, and then we can sample from that Gaussian and produce H, and then we can decode and check versus the ground truth signed distance field. So this is a variational autoencoder, right? And this is just to tell us, basically give us a lower dimensional encoding of the environment, because the environment can be very huge, especially in 3D. Then we feed that in along with the start and goal into another neural network. It produces a context vector we call C, And that goes into a normalizing flow. And again, there should be a picture of a Gaussian here. Don't know why it's doing that. And this Gaussian, we can sample Z's from this Gaussian, and given the context, decode those into use. So basically the idea is this tells you what problem you're solving. This brings in the randomness, because you want to generate many samples. And this makes sure that the samples are transformed in the proper way to be relevant to the problem you specify. Okay? And so that's how we do this. We minimize the expected cost minus the control entropy and the loss for the VAE. Okay, so far this is good, and I'll show you results. This actually works. But it's missing a key piece. And the piece is that we can't possibly cover the space of environments that we're going to encounter in the real world. It's like the space of images. It could be whatever, right? And if we give it an environment that's radically different from what we've seen, this produces garbage because we're out of distribution with respect to what we trained on. So how are we going to adapt to new environments? So we looked at this and we said, okay, well, oh, now the Gaussians are back. Hooray. Okay, great. So you saw what those are supposed to look like. All right, how do we adapt to these new environments? And what we did for this is first, we have to know how much to adapt. Because if we're already in an environment like what we've seen, we don't need to change it. So what we need then is what we call an out-of-distribution score. There are many ways to compute our OOD scores. Ensembles is a popular one. We used a slightly different one based on actually a different normalizing flow that I'm not going to get into the details of. But basically, it's a way to compute the probability of these environment encodings. Okay? And what's really cool about this particular method, this way of computing the probability, is that this probability measure is differentiable because this is all a flow model. Right? So I can differentiate through the OOD score. Why does that matter? Because I can minimize it. What does that mean? If I minimize this score by changing H, I'm effectively creating an environment that is more in distribution. Okay? So here's what that looks like. I'm encountering a novel environment, looks completely different from things I've seen before. Okay? And I encode that environment to H. I look at the OOD score. The OOD score says this environment looks nothing like what you've seen before. You're way out of distribution. If I use that H to produce trajectories, then I get very bad trajectories. Look, they're going through obstacles all over the place. Okay? So I want to change my representation of the environment so that I'm not in distribution. So I apply a gradient to produce lower cost trajectories, to update H to produce lower cost trajectories, as well as updates H to be more in distribution. So if I can do that, then what I'm basically looking for is to hallucinate a new environment representation that looks more like what I've seen before and also allows me to go through this new environment. And that's why what you see here early on, you'll see it restart, it's hallucinating these blobs. These are decoded H's that you're seeing. These blobs are like the spheres that we trained on in our training data, okay? And of course, once we pass the blobs, they're not relevant. But if the blobs are near where we are, they're basically blobbing out parts of the environment where we can't go, and we go between the blobs in order to go through these narrow passages. So we're basically hallucinating environments, but not too much so that relevant parts of the true environment are still represented. Okay, we built a sampling-based MPC method around this. This is, again, MPPI. This is a standard method in the literature where we just take samples from a Gaussian and add them to a nominal trajectory. Our method learns that distribution and it adds samples, but it also does some of this stuff. The reason is that this is really good for generating big changes in trajectories. This is really good for locally optimizing the trajectories, and we want both. So we include both of these in our MPC method. Here's some results, and I'll be done in just a couple minutes, so don't worry, it's not going to go too long. So again, these are training environments over here. This is for a double integrator, just doing planar navigation. And this is, a standard method, MPPI. And this is our method, including both MPPI, the flow part in MPPI, as well as the projection that I talked about to basically make things in distribution. It's not that every single trajectory avoids an obstacle, that's never been the goal, but it's that we get a wide selection of good trajectories in the samples. We then apply this to a 12-degree freedom dynamic quad rotor. You can see the quad rotor represented as this disk flying around spheres. But again, the real world doesn't look like spheres. Maybe there's some hallways or narrow passages we have to fly through. And again, we're using MPPI here and it gets stuck. Whereas if we use our method, we can basically adapt our representation of the environment to make our model useful, and it works there. But those are still simulated things. What if we just give it like a real world point cloud? This is a scan of a real world point cloud for a staircase that looks nothing like a set of spheres. But still, we're able to apply our method, this is our full method over here, to navigate through this radically different environment than we saw in the training data. A little bit of quantitative results. We tested versus 3 baselines, MPPI, Stein variational MPC, ICEM, and we tried with our projection and without. Of course, when we're in distribution on things like our training data, the projection doesn't help much. Sometimes it does a little bit. But when we go out of distribution on radically different things, then we see our method is outperforming the others, and in some cases by quite a lot. Okay, let me skip this a little bit and I wanted to show you some of the 3D hallucinated blobs that we generate when we do this projection method. So you can see it here. Again, if it's not near an obstacle, then the trajectories it's generating are pretty good. There's no reason to hallucinate, so you get kind of arbitrary stuff. But when it has to go through a narrow area, that's when it really has to hallucinate harder to get through. Okay, I also want to say we did apply this on a real-world robot as well. In subsequent work after that RSS paper, we applied this to a manipulator. Again, same idea, trained with a bunch of spheres. In the real world, you encounter a fridge, right? Nothing like a sphere, really, but you can generalize what you learn by adapting that H, as I showed you. Okay, so in summary, we learned a distribution for sampling trajectories based on normalizing flows, and it generates both goal-directed and environment-aware control sequences, and then showed you a method of how to adapt what we learned to a radically different environment. And it's able to adapt to these challenging environments, and even though it was trained on the very simple simulated set of spheres. Okay, so in conclusion, what I talked about today was how do we deal with this problem that we'll never be able to get a model that is going to be reliable in the entire state and action space. And specifically, we focus on 2 questions. Where can we trust our model? That's where we were doing the dynamics learning and saying, okay, here's a trusted domain, stay inside that, and you can track what you plan. And the second question, how do we adapt our models to new situations under which they wouldn't be reliable by Okay, so thank you very much for your attention. I want to finally say thank you so much to all the students in the lab. They're the ones who do the work and did all this great research you saw today. And also thanks to our very generous sponsors for supporting this work. Okay, I know we're a little over time. Sorry about that, but I'm happy to take any questions.
Okay, regarding the first section of your slides, so how we can guarantee that if you keep the samples inside the epsilon boundary, you can reach the goal target?
Okay, so how do we guarantee that? So there's the control part of that, and then there's the motion planning part of that. Which do you want to hear, or both?
So no, you reject the samples out of the epsilon boundary.
That's right, yeah.
So, and the samples come from the motion planning, yeah. So the output of the motion, but you reject them, some of them.
Right, so if you go outside the trusted domain, we reject it, and we don't use that sample. Is that the question? Or?
No, I mean, how we can guarantee that with this sampling you reach the goal?
Right, so sometimes you can't reach the goal. This goes to what I was talking about with connectivity. So in this cartoon figure, I showed you a space of d epsilon x that is nice and connected, and the start and the goal are in the same piece. But in this slide right here, I showed you actually 2 disconnected pieces. So if the start is here and the goal is here, you cannot find a path within the trusted, a trajectory within the trusted domain. And this is a big problem, right? You know, you can only do in this framework what your model is kind of certifying for you, and that may be conservative, right? It's probably possible for the robot to go there, but you just can't guarantee it, and so it won't be. Yeah.
I have a slightly related question. Thanks for the great talk.
Thank you.
I was wondering if there are any assumptions for your guarantee in this work on how densely you have to sample the space, and
Yes.
because you're assuming kind of a discrete dynamics model, is there like any possibility that dynamics flow up in between?
Yeah, so what if it's a hybrid system, right? You just get these big jumps, right? So I would go back to the assumptions at the beginning. We do assume that the true dynamics, I feel bad for you trying to keep up with the slides, but if you go to this slide here,
Yep.
you know, we are assuming Lipschitz continuous dynamics. But, you know, even that, I think, you know, there's more detail to that too, in that first, the ground truth dynamics actually isn't as important for the guarantees as the Lipschitz, as the error that we're trying to compute. So, you know, let's say that you have a function g that's really good at capturing those discrete changes. And so the difference between f and g is actually going to be very small. And that means the error is small, that means the Lipschitz constant is small. Right? So just because this has a lot of changes, if you capture them, it's no problem. If you don't capture them, big problem. Right? So you know, it's important to know that we're looking at the Lipschitz constants of E, not F. Of course, a very discontinuous F is hard to learn, and therefore there's a correlation between very difficult to come back, but it's possible with enough samples. Yeah.
Great talk. So you're using like this probabilistic method to estimate the Lipschitz constant.
Yeah.
It was kind of unclear from the GIF that you had, but are you actually like approaching it from above or below?
Yeah. So great question. Yeah, you really caught that detail. So the GIF you're talking about is, God, so many slides. This one, right?
Yeah.
Yeah. So this is a really important point, that when you have a small number of samples, you can fit to them, but it doesn't really mean much, right? And that's why this goodness of fit test is actually necessary. So when you have a small number of samples, this deviation between the fit and you know, the samples will be higher, and will create a large standard error. And we actually account for that in the bound. So when you have a lot of standard error, then we're going to overestimate the Lipschitz constant enough, well, a lot, to get this kind of probabilistic bound. Yeah, but yeah, if you see, it starts being below when you have limited data, but then it goes above. Yeah. Mm-hmm.
Does anything change or become better in this framework if you can, by construction, set the Lipschitz constant for your model?
For the G?
Yeah.
Yeah, okay, so just to get back here. Sorry. Right, so this is the way that we learn our dynamics, is simple neural network. There are neural network learning methods that explicitly try to bound the Lipschitz constant of the network. And we did try using some of them. They did not perform so well, so maybe, you know, there's some room for improvement in how we're applying those here. But this would give a more well-behaved G. But again, the issue is not so much that we care about G being well-behaved, we care about the error being well-behaved. So, you know, in fact, you might make the argument in some cases that, let's say I did have the kind of hybrid dynamics or really fast changes in the dynamics of my true system F, right? But now I'm trying to learn G and I want to impose a low Lipschitz constant on G. Well, then I can't actually fit those very discontinuous dynamics of F. So imposing a Lipschitz constant constraint on G might actually hurt the Lipschitz constant of the whole error. Yeah.
So is my understanding correct that the radius of those balls is uniform for all the points?
In this work, that is exactly right. In the follow-up work at CDC, it's actually per point.
Okay, so do you use like different Lipschitz, local Lipschitz constants?
Yeah, basically.
Okay.
Yeah. Yeah.
Thanks again for the great talk.
Mhm.
Just when you're getting guarantees about the control input, you have Lipschitz constants on G0 and G1. To compute those, does that mean that you need to sample with like no control input, and like does that change how you have to sample things, or can you generate those Lipschitz constants from the samples that you have? Because
I see. So how do I get different Lipschitz
Yeah, you're separating
constants
them out, right?
for this? Yeah, good question. So we do that. We get the Lipschitz constants of each independently by basically computing different parts of this G separately. I guess I'd have to check back on the paper with the details about the exact process for that. But we do get different constants for these two. Yeah.
I was wondering about the second half of your talk. That looks like amazingly interesting work, but one thing I noticed is for your generation and adaptation method, you kind of assume that you have a full map of the environment, right?
Yes, that is true.
Can or are you planning to adapt this to, for example, some sort of more local proprioception-based
Yeah.
view on the environment? Or
Yeah.
do you think that whole map is necessary?
Yeah, so that's a very, very good point. I think it's a limitation that we assume the whole environment, and I really would like to do it locally up to like some horizon, basically. There's some challenges with doing that, honestly. You know, the problem is when you're doing these projections, what do you do with the uncertain parts of the environment? How do you include that in your representation? So I'm not quite sure about how to do that yet, but it would be a very interesting thing to explore. Yeah.
So one more question. So do you see any connections between this method and methods that use traction theory?
Yes. So the question was, is there a connection to methods that use contraction theory? And in fact, this is exactly what Glenn did in the follow-up work. Okay, so many slides. I want to get to this part. Yeah, there we go. So, okay, I overshot. Here we go. Yeah, so basically, in the previous work, the one that I talked mostly about, the controller was really simple. It's just trying to do least squares, and you can use these like perturbation bounds to make some guarantees about it, and life is okay. But that's really limiting. Like it requires the state and action dimension to be the same, so it doesn't work for under actuated systems. There's a lot of problems. So the follow-on work to this, what Glenn actually did is applied contraction theory to basically get rid of those limitations. Now, I don't know who's familiar with contraction theory. I'm certainly not an expert in it, but the key issue with applying contraction theory is you have to learn this metric for the contraction to work, so that basically you contract according to this metric as the trajectory goes over time. And it's going to be different for different systems. So this was a key part of this work, is how do I learn this contraction metric so that I can get the guarantees of that system. But I'll have to refer you more to this paper if you want the details of that. All right, thanks so much. Yeah.